Hello guys, welcome back to the channel. Today we will be taking a look at a Math AHL question involving the sum and product of complex roots with polynomials as well. So let's get started with part A. So for part A, we have been given a function g of x, and we have been told that alpha, beta, and gamma are the three roots of the equation g of x equals 0, where they're all real numbers, and we have been asked to write down the value of the sum of these roots essentially. So this part is quite straightforward. We could actually use the formula negative b over a to compute the value for the sum of the roots. So basically in this formula, the a essentially is the coefficient of the largest degree term. So in this case, a is 2 and b is the coefficient of the second largest degree term. So the second largest degree over here is obviously 2, and the coefficient of x squared over here, or negative 7x squared over here, the coefficient is negative 7. So we can just plug this into our formula. So as mentioned before, b is negative 7, plug that in here, this becomes positive, a is 2, and our answer is 7 over 2, which is just 3.5. So moving on to part B. So for part B, we have been given another function, which is degree 5, and it's defined by h of z, and we have been told that alpha, beta, and gamma are also roots of the equation h of z equals 0, and that it is satisfied by the complex number z equals p plus 3i, and we need to show somehow that p equals 1. So one of the things that we can immediately deduce is that by using the conjugate root theorem, we can say that another root of this function is p minus 3i. This is just a property when you're dealing with complex roots. So this is basically the conjugate of this complex number over here. And our goal over here should be to try to perhaps formulate an equation involving the sum of the roots, and then solving p, and then eventually showing that p is equal to 1. So what we can do first is find the sum of all the roots of this function. So once again, we can use our formula negative b over a. So in this case, our b value is negative 11 and our a value is 2, as shown on the previous page. And by part A, we also know that alpha plus beta plus gamma equals 7 over 2, and now we basically have all the roots. So we have z equals p plus 3i, p minus 3i, and we also have alpha, beta, and gamma. So now what we can do is we can essentially add up each of these roots and put an equal sign and show that it's equal to 11 over 2, since it is a sum. This is the sum of all the roots. And since we know that alpha plus beta plus gamma is equal to 7 over 2, we can actually substitute this in here. So then we get 7 over 2 plus p plus 3i plus p minus 3i equals 11 over 2. And then over here, the 3i minus 3i, that cancels out. And if we move this 7 over 2 to the other side of the equation, we then end up with 2p equals, and then of course we get p plus p, so you get 2p over here, and then that's on the other side, so you get 11 over 2 minus 7 over 2 here. And if we simplify, that's just 2p equals 4 over 2, and which is just equal to 2p equals 2. And hence, if we divide both sides by 2 of this equation, we get p equals 1. So that's the basic idea over here. It's to try and use the given information to formulate an expression for the sum of the roots. We know that the roots are alpha, beta, gamma, and p minus 3i and p plus 3i. Those are the only roots of this function, since the degree is 5, so we can have 5 roots. And the basic idea is to use the information from part A, substitute this in here. The 3i and the negative 3i cancel out, obviously, and then we end up with 2p equals 11 over 2 minus 7 over 2, which giving us p equals 1. So moving on to part C. So for part C, we're given that h of a half is equal to 0, where alpha and beta are positive integers, and beta is greater than alpha, and gamma is a rational number. So for C part 1, we need to find the value of the product of alpha times beta. So this is the key in this question really. It tells us that we're dealing with the product of roots. So what we can do is first write down the information that we have. So we know that the roots of h of z equals 0 are obviously 1 plus 3i, since we showed previously that p equals 1. So we get 1 plus 3i, 1 minus 3i, which is the conjugate, a half, which is given over here, and the other two roots are alpha and beta. And over here, we can use the product of roots formula, which is negative z over a. So basically, the product of roots formula depends on whether the degree of the polynomial is even or odd. So in this case, since it is odd, this is a negative z over a. However, if the degree of the polynomial was 4, the product of roots formula would be z over a. So since the power over here is 5, it's an odd number. This is the formula that we use. So over here, z is the constant term, which we know, and a is the coefficient of the largest degree term. So we can simply substitute this into our formula. Z equals negative 20, a equals 2. If you simplify, this becomes positive 20 over 2 equals to 10. And now that we know the product of the roots are equal to 10, now what we can do is formulate an expression where we multiply each of these numbers and equate it to 10. So what we get is 10 is equal to the product of all these roots. So what we can do next is multiply both sides by 2, giving us 20 equals, and then we can expand this. So 1 times 1 is 1, 1 times negative 3i is negative 3i, 3i times 1 is plus 3i, and then 3i times negative 3i gives us negative 9 times I squared, and this alpha times beta remains the same. And then this cancels out, negative 3i plus 3i, and then I squared is negative 1. Negative 1 times negative 9 is just positive 9, and then we add this 9 with 1, giving us 10. So then we get 10 alpha times beta is equal to 20, and then we can divide both sides by 10 to isolate alpha times beta, which gives us alpha times beta is equal to 2. Yep. And so that overall idea is quite similar to the last question, where we're essentially the basic idea is to find the sum of the roots in the previous question and then use the actual roots and then essentially just equate it to that value. And the same principles are applied over here, where we can first find the product of the roots instantly by using this information, and then we write out all the roots that we know, and we simply equate the product of them with 10 over here. So for the last part, we're asked to write down the value of alpha and beta. So over here, the key for this question is that alpha and beta are positive integers, and beta is greater than alpha. So the fact that they're positive integers helps us. So that basically, since beta is greater than alpha, there can only be one possible combination. So it has to be that beta is 2 and alpha is 1, because there's no other combination that gives that satisfies these conditions. So beta equals 2 and alpha equals 1. I mean, if you had alpha equals negative 1 and beta equals negative 2, that obviously wouldn't satisfy this condition. So there can only be one possible answer to this. So alpha equals 1 and beta equals 2. Yep, and that concludes the end of this video. Hope you enjoyed watching, and if you have any questions, make sure to leave them in the comment section below. And thank you for watching.